Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present columnar data augmentation through visual analytics. Kava lets users augment their data with additional attributes found on knowledge graphs. To construct a new attribute, each row of a dataset is mapped to a node on a knowledge graph. Each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node.
to interactively explore and visually analyze large multivariate data. For example, this cosmological simulation that is clustered into dark matter halos. we create a probabilistic data model in each cluster. We present a complete visual analysis system based on this data representation, which is especially well suited for the density-based visualizations shown here.
We present a framework for the visual exploration of spine simulation data. We show the force distribution on spinal discs, enable assessments of imbalances, and reveal impact vectors that were not accessible before. This is a novel direction in medical visualization, and we hope that it might bridge the gap between biomechanical research and clinical application.
Traditional clustering tools do not include users in the analysis loop. We present PK clustering, a new approach for interactive clustering using VIS. First, users specify their prior knowledge. Several algorithms are run and match with the prior knowledge. Users then build a consolidated clustering iteratively with suggestions based on consensus, the graph, and their knowledge of the data. The result is a consolidated clustering.
Many techniques can be used to render and visually explore large 3D line sets with transparency. However, all these techniques differ in several aspects such as runtime performance, memory consumption, and image quality. In this work, we provide an extensive comparison study to discuss the advantages and drawbacks of transparency rendering techniques for large line datasets.
TaxIMIS is an interactive visual analytic system to help tax officers identify suspicious tax evasion groups. The system integrates the traditional data mining algorithm and visual analytics techniques. 4 coordinate views are provided to support interactive exploration of tax evasion evidence. We demonstrate its usefulness through case studies using real-world test data and expert interviews.
Visualizations are about visual patterns, but there's more, much more. We show the connections between more than 100 arguments on why visualization works. And don't forget to check out our website.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable x and low variable y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. We introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
How do user interactions lead to insights? We present a case study with a tool that supports 5 types of interactions for exploring drug-target relations. Through an evaluation, we collected interaction trails, manually extracted interaction patterns, characterized the user insights, and explored the relations between interactions and insights.
Hi everyone, I hope you're doing well. I'm Heikyu Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internals. Also, for a better understanding about adversarial attacks, it would be worthwhile to examine if and how an attack strength changes how the model produces incorrect predictions. For example, it would be useful to know if a stronger attack exploits the same neurons as a weaker attack does, or if those sets are completely different. We present Bluff, an interactive visualization tool for discovering and interpreting how adversarial attacks mislead DNN into making incorrect predictions. Our main idea is to visualize activation pathways within a DNN traversed by the signals of input data. For given input data, an activation pathways consist of neurons that are highly activated and the most influential paths. Activation pathways represent what features are detected and how those features are related to contribute to the final prediction. To understand how the attacks manipulate the neurons and the paths inside the models, Bluff visualizes the activation pathways of both benign inputs and attacked inputs. That is, Bluff finds and visualizes the most activated pathways given benign and attacked input data. Bluff also
Well, welcome everybody. Appreciate you coming to the graphs session. We have several talks lined up for today, all centered around graphs and analysis, and of course a little bit of visualization mixed in with that. Our first talk will be entitled Responsive Matrix Cells, a Focus+Context technique. This will be presented by Tom Horak.
Hi everybody and welcome to our talk. I am Tom Horak from the Interactive Media Lab Dresden, and together with Philipp Berger from the University of Rostock, we will present our work on responsive matrix cells. Philipp and I are joint first authors and worked on this project together with Heidi Schumann, Raimund Dachselt and Tominski. With our investigations, we aim to facilitate working with multivariate graphs. These graphs are challenging data type, as both structural and multivariate aspects are of interest at the same time, besides the traditional challenges of graph visualizations. This means an analyst needs to see how nodes are connected, but also how node attributes are characterized. Even further, the links themselves can also be detailed with attribute values. Importantly, the visualization should be able to provide an overview on the network, for example, allowing to see clusters or outliers. But also it needs to reveal the details for specific regions of interest. Finally, support for editing the graph is often desired as well, but rarely possible within the same tool. Of course, we are not the first that aim to address these challenges. There is a notable body of work on how to visualize multivariate networks out there. Here, Nobre et al.'s recent state-of-the-art article or Kaiyuan and colleagues' book are providing good overviews. However, the existing solutions are often optimized for one certain aspect, for example, showing the structure, or the multivariate aspects, or revealing the specific Hi everybody. For matrices, such as life-rate, same, or time cells.
As Tom just mentioned, our responsive matrix cells also allow for directly manipulating data attributes. This can be done by either typing a new value or dragging a mark. Effectively, this enables analysts to quickly correct data values or run what-if scenarios, all without the need of switching to a different view or even application. The question now is how all these concepts work together, both on a global and local level. To illustrate this, we will give you now a short tour through our prototype by exploring a soccer dataset. The graph consists of 95 nodes, which are the players. They are characterized by over 30 attributes. An edge exists between two players if they have played for the same club during their career. The edge weight corresponds to the number of same clubs. Here, we are sorting the matrix by the player's club affiliation, and select the attributes, appearances, minutes played, total shots and goals for the similarity calculation. What we can see now is that two players are quite prominently standing out in the similarity part, Lionel Messi and Robert Lewandowski. The two lines, with many reddish cells, are indicating that they are dissimilar to most other players, while the green cell at the intersection means that they are similar to each other. To study this pattern in more detail, we create a meta cell by selecting a subgraph around the green cell. We can now see the specific attributes of the respective nodes leading to the similarity encoding. Scaling up the responsive matrix cell adds axis labels to the chart. Via a quick axis menu, we can also change the visualization to get a different perspective, for example to a parallel coordinates plot. However, for now we want to specifically compare Messi and Lewandowski and switch to a unit cell setup. In the central unit cell, we can see that Lewandowski and Messi have the exact same number of appearances and roughly the same shot-to-goal ratio, although Lewandowski has played more minutes. By loading additional attributes to the chart, significant differences become visible. For example, Messi has twice as much ball possession and twice as many touches as Lewandowski. Let's have a look at the relations between them and see if they have played for the same club before. We can directly switch the responsive matrix cell to the adjacency part of the matrix. As indicated by an empty right unit cell, Messi and Lewandowski have never played together. To get a more intuitive representation of the connections, we can switch to a meta cell with an embedded node link diagram. Through interactive highlighting, we can find out that a path between Lewandowski and Messi exists in the subgraph via Thiago and Dembele. Looking at the red line for Messi, we notice multiple nodes that are particularly dissimilar to him. To take a closer look at them, we create a new unit cell selection. When switching to the star plot representation, we can see that multiple values are missing. To fix these, we enlarge the cells further. Now, we can access handles that appear at the marks in the visualization. These allow us to edit the data value and update it to correct one by simply dragging a handle or entering the value directly. During the editing, the star plot is updated on the fly, as are all other visualizations depending on the edited value, including the similarity part of the matrix. Afterwards, the analysis session can be continued seamlessly by defining new responsive matrix cells in the matrix. Using the prototype you just saw, we conducted guided hands-on sessions to receive early user feedback with 4 PhD-level researchers. 2 of them were interaction experts and 2 visualization experts. These sessions were held remotely via video chat with screen sharing and lasted around 1 hour. Participants received a short introduction and a demonstration of the prototype. Then they were asked to interact with the prototype and test the usability of its functionalities. While all participants agreed that initial training is required to understand both the dataset and the visualization approach, they quickly adapted and applied the techniques without larger problems. They indeed started to explore and reason about the dataset on their own. Feedback-wise, participants rated the experience very positive. They stated that unit and meta cells were indeed helpful for understanding the details. They also thought that being able to switch responsive matrix cells between adjacency and similarity is neatly bringing together the 2 worlds of structure and attributes. Editing and the immediate feedback was perceived as useful, especially for understanding the influence of attributes in the similarity measure. Difficulties occurred only when observing editing effects with larger responsive matrix cells, as they reduce the visibility of the remaining matrix. As illustrated by our live demonstration and the user feedback, we believe that responsive matrix cells are a promising solution for analyzing complex multivariate graphs. They enable workflows that seamlessly go from overview to detail to editing, offer a flexible definition of what, where, and how detailed information is shown, and are based on well-known concepts including focus and context, semantic zooming, direct manipulation, and responsive visualizations. Our responsive matrix cell approach has limitations with these base concepts. Responsive matrix cells depend on the ordering of underlying rows and columns, and our focus on context technique causes distortions of the base visualization. To address these, we integrate options to sort the matrix and provide coordinated highlighting between responsive matrix cells and the matrix. We believe that our approach can also be an interesting foundation for future work. For example, it may be promising to consider spatial aspects, such as embedding maps into responsive matrix cells for geospatial networks. Editing could be improved by allowing absolute or relative changes of groups, or providing guidance by indicating reasonable values. Also, more elaborate evaluations should be conducted to compare our integrated responsive matrix cells with classic multiple view approaches. For now, you can check out our online demo as well as our project website for more details. And with that, we thank you for your attention.
All right. Well, thank you, everybody, for the comments already coming through in the chat. Apologize for the video glitch. I guess we get new types of errors now that we're on a virtual conference. Tom was great and responding in there already. He's already posted a place where you can get a link for the full video and also a version that you can play with all by yourself. So thank you so much. If you have questions for Tom, don't forget to be able to post them to the chat. And we have a few minutes right now for a Q&A session. So I already have one from Michael. He says, have you ever thought about matrix reordering with upper and lower triangles simultaneously?
Well, I'm not quite sure what you mean specifically, Michael. Maybe you can clarify a bit better. What we have integrated right now is the possibility to order the matrix. So we have different order algorithms available, but you can pick to figure out the starting point for your exploration. So depending on what you're looking for, you can change the order. yes, so that's possible, and probably could also be improved with more different order facets and possibilities.
Okay, so lots of ways to order a matrix, and sounds like you've got some support in there already. Yalong from Harvard said, I saw different visualizations in the detail view. How did you choose which one to do?
So yes, we have a couple of visualizations available. So starting with simple bar charts with star plots, but also parallel coordinates, as well as a node link graph. Of course, you can fully choose what visualization you want to see, but this also might depend on where you're looking in the matrix. So for instance, if you're looking at the adjacency part, you might want to have a node link representation to get a better feeling of the graphical structure. And if you're looking at the attributes, you might want something like a bar chart or a star plot to get a better feeling. So this is something that you can fully switch. And also you can switch between embedding visualization for one single cell, but also having a visualization that spans multiple cells so that you can actually compare them and see their attribute distributions, for instance.
Nice. That sounds very flexible there. I had a question, right? So this editing, right, is one of the more novel components, this embedded editing. What are the use cases you see for actually doing that editing?
Well, I think often if you explore data set, you figure out that sometimes values are off because of faulty data or maybe also missing data. And by integrating this editing facilities directly into this tool, you don't have to go to a different tool or different view, but you just can simply fix these values. Or you could also play around with it and run what if scenarios. So what if this one attribute would be way higher? How would that be reflected in the overall matrix encoding?
I've certainly ran into both of those cases myself. When you're doing that, you're doing it with a very direct manipulation, right? You grab that bar chart, you move it up. Hey, there's more value there. Is that stored out somewhere? Can I then export that data set after I've done the manipulation?
Yeah. Right now, it's directly written into the data model, which is loaded in the application. We have not implemented a real export functionality right now, but this could be added, of course. And the source code is also available. Christian posted the link in the Discord chat. So if you want to add it to the prototype, feel free to do so.
Okay. Another question related to direct manipulation, right? So related to editing, you showed that direct manipulation. Did you try other things that didn't work so that if somebody's looking at direct manipulate or at editing, they might avoid a blind alley?
Not really. So right now we focus on the basic functionalities, how you could edit these values, and this is either by dragging the bar up and down or by entering just a value via your keyboard. But in general, more in-depth studies, how this tool would be used by data analysts is still up for future work.
All right. Well, thank you very much, Tom. Everybody feel free to supply virtual applause in the chat box there, but that was a very interesting presentation. We're going to transition now to the next talk. This is exemplar-based layout fine-tuning for node link diagrams by Jiacheng Pan.
Hey everybody, thanks for watching my talk. I'm Jiacheng Pan from Zhejiang University. My talk is about graph visualization and interactions. We presented an exemplar-based layout fine-tuning approach for node link diagrams. Generating appropriate layouts of graph data has been a major research topic over the past decades. Among many solutions, node link diagrams are widely used. According to taxonomy by Gibson et al., graph drawing methods can be categorized into three main kinds: force-directed methods, dimension reduction methods, and multi-level methods. However, additional layout optimizations or manual modifications are typically required to improve readability according to the visual aesthetics. The aesthetics of a graph layout is often subjective and may vary with user preferences. Modern rule-based graph layout methods have successfully integrated user preferences into layouts. Fisheyes also modify layouts to reveal connectivity and topologies based on some specific rules. However, they are not aimed to specify individual node positions, so that they cannot meet some specific user preferences in many cases. In particular, fine-tuning of individual node positions in a layout has to be manually performed, which is laborious and time-consuming. How to reduce manual layout tuning effort. In many cases, we need to move some similar substructures into the same shape again and again. If we only need to move one structure as an exemplar and transfer modifications to other substructures, we can greatly reduce the fine-tuning effort. So we proposed an interactive exemplar-based tuning approach to reduce laborious and repetitive layout modifications on similar substructures. The approach works as, given a graph with an origin layout, we can first specify a substructure as an exemplar. Then, we can specify some similar substructures. According to our preference, we modify the exemplar into a new layout. Our interactive tuning approach can transfer modifications on the exemplar to the similar substructures. Next, I will explain its details. In this presentation, I will color the exemplar in red and color those similar substructures in blue. First, we pre-layout the entire network and compute node embeddings. Then, the user can specify an exemplar and some substructures similar to it. Next, the user modified the exemplar's layout. Our modification transfer technique can transfer the modifications made on the exemplar's layout to a similar substructure. Finally, all the modified layouts are merged into the global layout. As our approach transfers modifications on one exemplar to its similar substructures, how can we specify similar substructures? Besides lasso interactions, we utilize the similar substructure retrieval technique proposed by Chen et al. To query similar substructures. First, we generate a low-dimensional embedding for each node using GraphWave. The user can specify an exemplar from the entire graph to search substructures similar to it. First, we search k nearest neighbors for the exemplar's nodes in the embedding space. As we know, embeddings generated by GraphWave captures node topology information. So these k nodes can form similar substructures because their embeddings are similar to the exemplar's nodes. Then I will explain about modification transfer. Before the explanation, we first give some definitions. Here we define the red structure as the source and the blue structure as the target. The user can modify the layout of the source into a modified source. Our modification transfer technique transfers user modifications on the source layout to the target and obtains a modified target. Yes, here I use the definition source to replace exemplar just for symmetry. Let's go into the details of modification transfer. We first build injective correspondences between the source and the target using graph matching methods. One correspondence contains one source node and one target node. Many graph matching methods rely on node positions. So before computing correspondences, we relay out the source and the target with a force-directed algorithm. However, sometimes graph matching methods cannot build correct correspondences because they try to find a corresponding node for each node, even their correspondence is not correct. We designed some strategies to filter out these incorrect correspondences, which can be found in our paper. With these correspondences after filtering, we first try to move the target to simulate the shape of the source. Suppose only 3 pairs of nodes, 2 nodes A, 2 nodes B, and 2 nodes C are preserved as correspondences in this case. The first step is aligning. The aligning step translates, rotates, and scales the layout of the target to minimize the dissimilarity to the source. It solves a minimization problem whose target is to minimize the sum of distances between every pair of corresponding nodes. The second step is deforming. We first move nodes in the target to the position of their corresponding nodes. For example, in this case, we move the blue A node, the blue B node, and the blue C node into positions of their corresponding nodes. At the same time, we try to preserve the original layout of the target. We minimize the distance change between any two nodes in the target using stress majorization and produce a new layout. The third step is matching. The matching step constructs new node correspondences between the source and the target according to node positions. We first select several pairs of nodes which are close in the Euclidean distance and use the Hungarian algorithm to choose a set of injective correspondences with the least distance sum. In this case, the red source node D can map to both blue target nodes D and F, and the red source node E can map to both target node E and I. And finally, the Hungarian algorithm chooses two nodes D and two nodes E as correspondences. We deform, match, deform, match, until normal new correspondences are built. Finally, we move the layout of the target to a new shape similar to the source and get a new set of correspondences. Let's look back to our layout simulation technique. With a source, a target, and their correspondences, we can move the layout of the target to simulate the layout of source and construct a new set of correspondences. Finally, we perform another round of layout simulation to transfer the source's modifications to the target. And we finally get a modified target structure whose layout is similar to the modified source structure. After we modify the substructure's layout, how can we merge it back into the entire layout? The merge process is similar to a deforming step in the modification transfer. We use stress majorization to smooth the procedure to prevent abrupt merging. We performed an evaluation to measure whether our approach improves the accuracy of the correspondence building. We prepared 3 datasets which are commonly used in testing graph matching methods. They contain several pairs of graphs with manually labeled correspondences. Note that we relay out these graphs with a force-directed algorithm. The result shows that our method performs best in most cases. I will show a video to demonstrate how our fine-tuning approach works on a real-world dataset. A graph is generated from the multi-stage stochastic financial modeling. It consists of around 70,000 nodes and 200,000 links. It is observed that there are several donut-like substructures. A substructure is specified as an exemplar for fine-tuning. Utilizing the pre-computed representation, similar substructures are retrieved. We find that these substructures are potentially isomorphic. Because their overall layout quality is poor, it is hard to investigate their topological connections. To fine-tune the donut subgraph, substructures around it are specified as target substructures. The exemplar is interactively modified into a layout with a distinguishable structure. After modification transfer, these substructures are more clear. Modified substructures are merged into the entire graph. For more details, please see our paper and video. We also performed a user study to verify whether our modification transfer technique can reduce human error. We prepared 5 exemplars and modified them into new layouts. For each exemplar, we prepared 3 target structures and asked the participants to fine-tune these target structures using 3 different techniques: dragging node, our technique with user-specified correspondences, and our technique with auto-generated correspondences. We recorded their completion time and number of interactions. The result shows our automatic technique performs best in both 2 measurements. At last, let's review our work again. In this work, we propose a novel layout fine-tuning method that can simultaneously adjust the layouts of multiple similar substructures according to user preferences. The key to the method is an efficient modification transfer algorithm that can transfer fine-tuned results of an exemplar substructure to other topologically similar substructures. Also, we conduct a set of quantitative and qualitative experiments that evaluate the efficiency of our approach. Thanks everyone, and any questions?
I see question.
So thank you, Jiacheng.
Yeah.
Right, there is, again, just a reminder for everybody, questions, please put it into the Discord chat. There's already one there.
Yeah.
Says, selecting groups of nodes may have different neighboring structures, even though they are in the same motif. This may cause a new problem for the new layout after the tuning, overlapping with neighbors. Do you think what do you think of this situation? How would you deal with that?
Yes, I ran into this situation in my real cases. So I did a merge. So I did a merge process after I fine-tune out these structures. The merge process using a stress majorization to preserve the original layout. So I think if two layouts are not overlapped before, they will not be overlapped after fine-tuning. Yeah.
So it basically avoids creating new problems. So maybe there was a problem there before, it would still be there, but it wouldn't make a new one. All right, that's a nice solution to that. Right? I really like the starting with the user provided layouts. When you showed you could add some more ones that maybe didn't automatically identify. Can you then have it like try and find even more in the network after you identify new pieces?
Sorry, what kind of new pieces?
So you had an example where it had where you had selected
interaction.
Yeah.
Yeah.
The interactive selection. Can you tell it to like expand the places it's automatically identifies to apply the layout to?
Yes.
Okay. There's another question in the chat. This will be the last question, I think. It says, what do you think about edge routing exemplars?
Edge routing exemplars. Sorry, I don't understand what is edge routing exemplars.
I'm going to put words into Sabin's mouth here, but you showed examples where you moved nodes around. What if you actually controlled the path of the edges as opposed to just controlling the node positions? Is that something that this technique could be applied to or extended for?
I think it may be a technique to modify the exemplars layouts, but we didn't consider this technique. Yes.
Okay. Well, hey, there's something to work on next, right? Thank you. Thank you, Jiacheng. Appreciate your presentation. Much applause in the chat would be completely appropriate as we need to move on to the next presentation. The next one is DRGraph, an efficient graph layout algorithm for large-scale graphs by dimensionality reduction. This will be presented by Minfeng Zhu.
Hello everyone, I'm Minfeng Zhu from Zhejiang University. It's my honor today to talk about how to visualize large-scale graphs efficiently. Graphs are universal data structures to present complex relational data in multiple domains, such as deep learning, social networks, and Internet of Things. Node-link-based graph layout is an efficient method to depict the overall structure and review relations. However, the understanding of the graph data is strongly influenced by the layout. It is common to assume two close nodes have high proximity even though there are no links among them. Therefore, preserving the neighborhood is an essential concept of graph layout. Efficient layout of large-scale graphs remains a challenging problem. Although force-directed methods are simple and easy to implement, they are not good at preserving local structures and may converge to local minima. Nonlinear dimensionality reduction-based methods aim to preserve the local neighborhoods. However, they suffer from the high computational and memory complexity. There are two main classes of force-directed methods. The spring electrical model assigns attractive and repulsive forces between nodes. The energy model formulates the layout of graph data as an energy system. Multi-level methods use the layout of the previous graph as an initialization for the next larger graph. Graph layout by dimensionality reduction methods can be classified into projection and distance-based methods. Projection-based methods have two stages. First, embed graph nodes into a high-dimensional space, and then project vectors into low-dimensional space. Distance-based methods aim to embed the local graph distances directly. Graph layout methods are tied by an optimization problem that minimizes the difference between the graph space and the layout space. Connection nodes with high node similarity should preserve high layout proximity in the layout space. A loss function models the difference between the node similarity and the layout proximity. However, TISNet fails to handle large-scale graphs due to the following three reasons. First, TISNet needs to measure graph distances between all node pairs. All pairwise distances requires V multiply V plus E computations using the breadth-first search. Second, computing the node similarity needs to sum over all graph distances. Third, the gradient requires all pairs of layout distances. Therefore, TISNet has a quadratic computational complexity and needs quadratic memory consumptions to store pairwise node similarities. We propose DRGraph to achieve the efficient layout of large graphs with three new schemes. First, DRGraph utilizes a sparse graph distance matrix to simplify the computation of pairwise node similarities. We use the shortest path distances between a node and its k-order nearest neighbors. Thus, computing the node similarity using the sparse graph distance matrix has a kV computational complexity. Second, we employ the negative sampling technique to compute the gradient based on a subset of nodes. The gradient of TISNet can be split into V attractive forces and V repulsive forces from other nodes. By leveraging the negative sampling technique, the gradient of DRGraph shows that each node receives 1 attractive forces and m repulsive forces. Consequently, the negative sampling technique reduces distance calculation from VV to MV. Third, We propose a multi-level process to accelerate the optimization of the objective function. We generate a series of causal graphs G0, G1, G2, Gn with decreasing sizes. The optimal layout for the closest graph can be found cheaply. The layout on the causal graphs are recursively transferred to the final graphs, with further refinement at each level. The refinement steps are fast due to the good initialization. Conventional multi-level techniques draw each graph level individually. We optimize all graph levels jointly by sharing information through the multi-level representation. We pre-compute the node similarity between nodes of graph G0 just once before optimization. We forward the computed gradient of graph G0 to graph Gn and backward the layout as an initialization. In summary, DRGraph enhances the nonlinear dimensionality reduction process with 3 new schemes. We approximate graph distances and node similarities by means of a sparse distance matrix. Then, we estimate the gradient by using the negative sampling technique. Furthermore, we accelerate the optimization process through a multi-level layout scheme. By integrating these 3 schemes, DRGraph achieves a linear complexity for both the computational and memory consumption, 1k equals to 1. We employ 6 metrics to evaluate the graph layout quantitatively. Colors encode the relative value on the same row. For all approaches, the running time only includes the layout time without data process steps. PMDS is the fastest method due to the pivots used. FM3 PMDS and DRGraph are much more efficient than others. They are comparable in terms of the running time on large graphs. Our DRGraph runs faster than PMDS on the Horak dataset because the performance of PMDS is severely affected by the number of edges. Our single-thread version of DRGraph is faster than GPU-accelerated testnet. The memory usage denotes the maximum usage of the process during its lifetime. FM3 and SFTP fail to visualize the Horak dataset due to their huge memory consumptions. DRGraph can easily scale up to large graphs with millions of nodes on commodity computers. Neighborhood preservation measures the neighborhood similarity between the graph space and the layout space. DRGraph and testnet are superior to other methods in terms of neighborhood preservation due to the local structure preservation nature of testnet. The gap of neighborhood preservation metric between testnet and the DRGraph is small, indicating that our method achieves a comparable layout quality. The normalized stress measures how the graph layout fits graph theoretical distances. DRGraph can achieve a better stress quality compared to testnet. FM3 reaches the best stress quality on large datasets. This is not surprising, because our algorithm does not optimize the stress. The crosslessness metric encourages graph layout methods to minimize the number of edge crosses. The minimal angle metric quantifies the average deviation of the minimal angle from the ideal angle. DRGraph and SFDP achieve the best performance in terms of crosslessness and the minimal angle athletic metrics. In summary, DRGraph achieves a comparable layout quality to FM3, SFDP, and TSNet. We show representative graph layouts of 4 large networks. We compute the edge length from the layout space and use the red to green to blue color map to encode the edge length. DRGraph generates clear clustering structures than FM3, SFDP, and PMDS on large networks. Please find more examples in our paper. In this paper, we present an efficient graph layout algorithm with sparse distance matrix, negative sampling, and multi-level layout scheme. Our DRGraph has a linear computational complexity and memory complexity. Experimental results demonstrate that DRGraph achieves a significant acceleration and generates comparable layout quality. The source code of DRGraph is available at GitHub. Thank you for your attention.
Thank you, Minfeng, for that presentation there. We have a few minutes for questions still, so please put them into the chat as you come up with them. I'm going to start off with one. So you showed examples of large scale structure being preserved in there, and that was, I mean, that was really nice. I was curious, if you zoomed in on it, how does it do with the small scale structure? Does it pull out nice features there too?
When we zoom into details, generally our DRGraph will generate a very fine layout, but there is some issues in our algorithm, such as we have some very large edges because we use negative sampling technique that reduce the gradient computation greatly, but which makes the gradient very unstable. So there are some nodes placed very far from its optimal position. So a little very long edges will exist in our graph layout, but we have a very general better graph layout overview.
No, it's a very nice overview. That, I mean, I was very impressed with that piece there. Have a question in the chat. It says, do you measure how well DRGraph improves graph cluster metrics, such as Jacquard, to measure the level of cluster overlap?
Oh, we currently we have not compared the graph cluster metrics. So we have used a lot of graph layout metrics, but we have not compared the graph cluster metrics. Maybe we will compare these metrics later.
All right. And then one last question. How do you define it is good or not when you get the coarsening graph? Can you keep important information?
The graph coarsening process, it is a little randomly because we randomly choose a node and Cottam graphs with its neighborhoods. So we can't define this graph clustering process is good or not good. So we only define the quality of graph layout finally. And the graph clustering process will keep the backbone of the graph, which keeps some important features of the graph, such as the overview and the backbone of the graph, which will accelerate our graph layout process greatly.
Okay. All right. Well, thank you, Minfeng. As always, appreciate all of the comments, and we need to switch over to the next talk now.
Thank you.
All right. So our next presentation will be by two people. This is on the scalability of network visualization from a cognitive load perspective. This is Vahan and his colleague Jian.
Hello, I'm Vahan Jian, and I will be presenting the paper titled Scalability of Network Visualization from a Cognitive Load Perspective. I will talk through the first half of the presentation, and my colleague Yalong Yang from Harvard University will present the second half. I would like to acknowledge our co-authors, Tim Dwyer, Lee Lawrence, Michael Wybrow, and Kim Marriott from Monash University. Showing a large number of data points as marks is a challenge in any visualization design. I can categorize scalability challenges into 6 categories: monitor resolution, visual metaphors, interactive techniques, data structures, algorithms, and human perception. Yet human perception, and in particular the effects of cognitive load, is understudied in graph visualization. Node link diagrams are used to visualize relational data. Nodes are used to represent objects, and links are used to represent relationships between these objects. Similar to other visualizations, beyond a specific threshold, node link diagrams become unreadable and resemble hairballs. There has been a lot of research exploring the effects of layout features for node link diagrams on readability and task effectiveness. Jian et al. Present an exhaustive survey of such studies. Even though there have been several studies to evaluate the visual scalability of node link diagrams, they rarely significantly vary the size of the networks. Also, instead of looking at the general limitations of network visualizations, most studies are tailored to evaluate or show the limitations of a technique that is being tested. To our knowledge, physiological measures have been rarely used to evaluate data visualizations, such as the study by Anderson et al. That measure cognitive load in participants when identifying the larger interquartile range on different types of box plots. Another example is the study conducted by Peck et al., which compares the task difficulty of estimating differences between 2 highlighted sections in bar charts versus pie charts. However, none has been used to evaluate network visualizations. Neuroscientists have identified different brain regions that are associated with various functions. Knowing which parts of the brain are involved in visualization tasks would help us understand and better evaluate cognitive load. To our knowledge, no previous study has investigated brain activity for a network visualization task. We wanted to explore the threshold of complexity, at which node link diagrams become useless without interaction or aggregation. However, we did not want to solely rely on performance measures and self-reported difficulties of the participants. We devised and conducted a user study which would help investigate human perception with respect to variations in size of node link diagrams. We generated scale-free networks of varying sizes, starting at 25 nodes up to 175 nodes in increments of 25 nodes. We used 3 densities, a factor of 2, 4, and 6, thus having 21 networks. We also generated 2 instances of each network, resulting in a total of 42 networks. The diagrams were created using the force-directed layout of WebCola. All the drawings were displayed in the same size for all participants and trials. The participants were not allowed to zoom in or interact with the diagrams. We decided to limit the study to 1 task, so that we do not have to worry about the differences in the intrinsic difficulties of each task. In addition to being one of the most commonly used tasks in network visualization studies, finding the shortest path is also proven to be effectively performed on node link diagrams. We pick 2 nodes for each graph by selecting the node furthest away from the center of the diagram and then highlighting the nearest node on the opposite side of the vector. We ask the participants to count the number of nodes on the shortest path between these 2 highlighted nodes. In this example, there are a total of 6 nodes on the shortest path. It is common to find multiple shortest paths between 2 nodes. In this example, there are 6 different paths. The study had 22 participants with backgrounds in computer science, all of whom reported that they were familiar with the task of finding the shortest path between 2 nodes in a node link diagram. In addition to performance measures, such as accuracy, response time, and self-reported difficulty, we measured heart rate variability, brain activity, and pupil dilation. The equipments we used were non-invasive.
Thanks for Han for presenting the first part. My name is Xiaodong from Harvard University. I will take over here to present our data analysis and results. We will first look at some traditional measures, for example, accuracy. We use x-axis to represent the increasing number of nodes in a graph. We recorded 3 types of results from our participants, correct and wrong answers. We also allow participants to choose unsure if they struggle to give an answer. The y-axis shows the percentage. We use a stacked bar chart to show the distribution of each type of responses. This figure shows how the accuracy changes in a graph density of 2. Graph density is the number of links divided by the number of nodes. We also tested graphs in different densities. As what we would expect in all graph densities with increasing number of nodes, the accuracy generally went down. You may also notice that for large graphs, the accuracy was even close to 0. While for the smallest graph, our participants achieved a high accuracy. We do this on purpose to cover a wide range of graph sizes. In this way, we were able to capture a wide range of other measures we are going to talk about. Let us then look at another commonly used measure, self-reported difficulty. We ask our participants to rate in 9 points Likert scale for each trial, from very easy to very difficult. Here we use the same type of chart to show the distribution. Like the accuracy, the trend is predictable. There is an overall positive correlation between the number of nodes and the reported difficulty in all graph densities. We also recorded the time our participants spent on each trial. Here we use error bars to represent the 95% confidence interval. Comparing to the previous 2 measures, this one looks a bit surprising. In the first stage, with the increasing number of nodes, participants spend more time on the trials. However, at a certain level of difficulty, the time decreased. Our explanation of this is that when the complexity of the trial increased to a certain level, people started to give up after some initial attempts, so the overall time dropped. In the literature, self-reported difficulty was the most widely used measure for cognitive load. Here, we use a different perspective to look at this measure. We divided every participant's responses into 2 categories, easy and difficult, based on their self-reported difficulties. We then aggregate the EEG data for these trials. Here is the EEG topographic map for the easy and difficult category. The color stands for the strength of the EEG signal. We can see clear differences between some brain regions, like the marked ones. To see the differences more clearly, we create a topographic map showing the differences between difficult and easy. We highlighted the electrodes that had a clear differences on the right. Different brain areas have different functionalities. Here we present information we collected from the literature. We can see these regions are associated with functions like decision-making, problem-solving, motor planning, visual spatial processing and perception, lower-level visual processing, and memory. These functions are required for completing our tasks. In the described analysis, we only have 2 categories, easy and difficult. To obtain a more nuanced understanding of the physiological measures, we need to extract a uniform measure for the trials. We call this hardness. We believe the hardness is reflected by the traditional measures, that is accuracy, self-reported difficulty, and time. One way is to extract a latent variable behind them. So we use the principal axis factoring to extract the hardness from the three traditional measures. Next, we are going to look at the relationship between hardness and the physiological measures. Let us first check the relationship between EEG and the hardness. We choose the electrodes that we identified in our preliminary analysis. The x-axis is showing hardness from easy to difficult, and the y-axis shows the normalized EEG power. It had a similar trend as time. For most electrodes, it went up and down. We conjecture that it is because once the task becomes very difficult, participants switched off and no longer make the effort to find the right answer, so cognitive load decreased. Following the literature, we also collected the pupil dilation as a proxy measure of cognitive load. The pupil dilation also shared a similar pattern with the EEG and time. Let us then look at the heart rate variability. It is also a commonly used measure for cognitive load in the literature. The trend was slightly different than the previous ones. It went up and down just like the EEG and pupil dilation, but it went significantly up at the hardest level. This is possibly because that heart rate is also influenced by frustration and anxiety. Participants' cognitive load decreased, but frustration or anxiety was increased, resulting in the overall increase. We first look at how to extract the hardness from traditional measures. We also look at how the physiological measures affected by the hardness. But it is unclear what affects the hardness. In the experiment, we explicitly controlled the number of nodes and the density because these are the two measures widely used in the literature in graph visualization user studies. However, we would like to investigate the other graph and layout features in the datasets we generated. We divide these features into three groups. First one describes the size of the graph. It contains number of nodes, number of links, and density. Second describes the crossings from various perspectives. Please see our paper for details. The last type contains features related to the shortest path. We use the linear model to find the relationships between these features and the hardness. Here we demonstrate the top 12 models with just one predictor. We can see the top 2 predictors are the features for graph size, and the later 10 predictors are features for crossings. We also run linear model with 2 predictors. We found adding one predictor can improve the model's accuracy significantly. The top model was combination of size plus crossing and shortest path plus crossing. We also run models with 3 predictors. However, there is no significant improvement on model accuracy. In summary, we identified the upper bound of complex graph people can read. We found regions that possibly associated with finding the shortest path task. We also found cognitive load increased with task hardness until a threshold, after which it decreases as the user may give up and put less efforts in. We built models between hardness and graph features. We found global features had a greater impact on hardness. Thank you very much for your attention.
All right, so thank you, Vahan and Yalan. That was really nice extension into human factors. I got a question in the chat right now. It says, "Am I right that most trials in the study have more than one shortest path?"
Yeah, let me answer that. Thank you for the question, Kunting. It is true that it will affect, and that is one of the factors we considered in our evaluation. So we, in addition to just the node size, the order of the graphs and the density, which is number of nodes, number of edges, we also considered multiple graph metrics. And one of those was how many shortest path possibilities were there in each graph. We considered 20 metrics overall. There's more details in the paper, specifically figure 10 outlines what metrics, like what are the examples of the metrics we chose.
Oh, very nice. Sounds, very thorough. I'm super excited. Unfortunately, that was really all the time we have for questions on this paper. I hope that we can see some of this, the results of this human factors work inform some of the algorithms that we're seeing made as well. We do need to transition to the next paper, though. So
thank you.
So our next paper will be a visual analytics framework for contrastive network analysis. This is Takanori Fujiwara.
Hello everyone, I'm Takanori Fujiwara from UC Davis. Today I will be talking about a visual analytics framework for contrastive network analysis. Finding unique characteristics in one network by comparing it with another network is an important analysis task. For example, by comparing Alzheimer's disease and healthy brain networks, we can understand their functional connectivity differences. To perform network comparison, many researchers introduce various methods. One approach is providing a detailed level comparison by visually comparing multiple networks. Another approach is using some statistics, such as the frequency of graphlets. However, the left approach requires one-to-one matching between each pair of nodes in different networks, called node correspondence. On the other hand, the statistics-based approach cannot compare networks at detail levels. In this work, we focus on the comparison of two networks, and we want to identify the unique characteristics that can be found in one network but not in another network. We call this analysis contrastive network analysis. To perform such analysis while solving the problems in the existing methods, we introduce a visual analytics framework, Contrana. We integrate contrastive network representation learning into Contrana in order to provide algorithmic support to identify the network's unique characteristics. This approach does not require the information of node correspondences, and it also allows the detailed level comparison. Additionally, we design interactive visualizations to supplement functionalities of contrastive network representation learning. I will explain the details of these 2 points. First, I will explain contrastive network representation learning. It utilizes 2 machine learning schemes. The first one is network representation learning, which extracts latent vectors from a network as shown in the figure here. The second scheme is contrastive learning. Contrastive learning finds more salient patterns in a target dataset relative to a background dataset. For example, in this figure, by contrasting images containing both handwritten digits and grasses with images only containing grasses, contrastive learning can extract salient features in a target dataset. There are several contrastive learning methods, such as contrastive principal component analysis. Contrastive network representation learning integrates these 2 schemes. I will explain how it utilizes the 2 schemes. To know the uniqueness of a target network, we want to compare the target and background networks, both of which can be represented as agency matrices. From agency matrices, by applying network representation learning, we can generate feature matrices. By doing this, we can extract comparable features between 2 different networks without knowing their node correspondence. From these obtained features, we can apply contrastive learning to obtain a projection matrix. This projection matrix contains the information of the target network's uniqueness. Lastly, by using the projection matrix, we can project the target network into a low-dimensional space. For interactive visual analytics, providing interpretability is critical. Thus, we employ an interpretable version of contrastive network representation learning, which uses LeapGL and contrastive PCA as learning methods. Please refer to our other work for details. Here is an example of round result. The left shows a contrastive representation, and the right shows the information required to interpret the contrastive representations, which includes definitions of features and features contributions to each component. Contrastive network representation learning can help identify the target network's uniqueness, but there are several limitations. The first and most critical limitation is that from only contrastive representations, it is difficult to know whether a target network has a uniqueness or not, and which nodes relates to the uniqueness. The second problem is that even though we have the information to interpret the results, understanding these direct output is not straightforward, because there could be many features with complex definitions. Lastly, even if we solve these problems, it is still not intuitive enough to directly analyze contrastive representations, because they do not provide the context of network structures. Therefore, in Contrana, we enhance this method to overcome its limitations. For the first problem in identifying the uniqueness, we design a new visualization for contrastive learning. For the problem of interpretability of features, we enhance the interpretability with intuitive visual representations. For the third problem, we relate learned results to commonly used network visualizations. We also address one more limitation that relates to the algorithm parameters. For this, please refer to our paper. I will explain more details for the first 3 points. For the first problem, similar to the existing works, comparing the result obtained by ordinary and contrastive learning method is a potential solution. For example, by comparing PCA and contrastive PCA results, if we can find clear pattern differences, we can say that contrastive PCA finds the target dataset's uniqueness that PCA does not find. However, in practice, this approach does not work well, because in many cases, we cannot see the clear differences between patterns obtained by PCA and contrastive PCA as shown here. Also, even if we see the clear differences, we still do not know which region is highly related to the target dataset's uniqueness. These problems are mainly because we do not know how nodes in a background dataset distribute in the same space with the target dataset. Thus, we should visualize background network nodes in the same plot. Here are the plots with background network nodes. In these embedding spaces, the target networks has much higher variances than the background networks. These results show that contrastive PCA successfully found the uniqueness of the target networks. Also, similar to PCA, a distance in a contrastive PCA result represents a dissimilarity between nodes. Thus, based on the distance from background network nodes, we can identify which nodes are highly unique, as annotated with red boxes in the figure. But how can we obtain background nodes positions in the embedding space of the target network? This can be achieved in a straightforward way, because we already have a projection matrix. With a background network's feature matrix, we can project background nodes in the same plot. Next, we enhance the interpretability of learned features and components. Here I will provide only a brief explanation. For more details, please refer to our paper. As shown here, DeepGL could produce a complicated feature denoted with multiple mathematical symbols. The middle figure shows how feature value is computed from one node annotated with orange. By summarizing this computation flow by directed links and text, Contrana provides a more intuitive way to understand the node feature. Now we can visualize a list of complicated features as shown on the right. The remaining information for interpretation is each feature's contribution to each component. We scale these values between -1 and 1 and visualize them as a heat map. A feature either being close to -1 or 1 has a strong contribution to the corresponding component. Lastly, in addition to the visualizations I have explained, Contrana provides commonly used network visualizations, including probability distributions, and node link diagrams of target and background networks. By visually linking all the views, we can effectively relate the learned results to the familiar visualizations to understand the result with the context of network structures. Now, I will demonstrate one representative case study. In this case study, we compare two protein-protein interaction networks. Both networks represent the same ETH interactions, but they are identified through different methods. From these two networks, we will find the uniqueness of the target network. We first highlight background network nodes and can see them only around the center. On the other hand, target network nodes are widely distributed. From a difference in the scatteredness, we can say that the target network seems to have some uniqueness. Also, we can see that feature 9 has the highest contribution to the first component. Feature 9 relates to the cut centrality, which measures how strongly a node influences the other nodes. Also, we can see that the target network has relatively high feature values for the left and right direction of the first component. We first select the left region and see the detailed structures in the laid-out network. We can see that the nodes in the left region are strongly connected to each other. Next, we select the right region. This time, we can see that the nodes are in a weakly connected region. However, if we look at the background network, the high value nodes can be only seen in a strongly connected region. Therefore, from these observations, we can say that the uniqueness is derived from the fact that a target network has two different types of nodes linked to the high cut centrality nodes, either a strongly or weakly connected region, which cannot be seen in the background network. We also evaluate the usability of Contrana with the controlled user study. Generally, the user study results show that when the target network has uniqueness, the participants successfully find and explain the uniqueness. I also want to share one important discussion from the user study. Some participants ask how much separation is enough to define the target network's uniqueness. This implies that we face with some ambiguity when identifying the uniqueness. For example, probably many analysts will feel the left figure has enough separation to confirm that a target network has some uniqueness. However, for the other two figures, this is less clear to conclude the result. This limitation should be addressed in the future. Finally, I'd like to conclude my talk. This work presents a framework, Contrana, which integrates and enhances the contrastive network representation learning to perform contrastive network analysis. In the future, we would like to extend this framework to compare two groups of multiple networks. Thank you for listening.
Thank you very much, Takanori. That was very interesting work. I'm super excited anytime I see comparison directly addressed in visualization work. Please provide questions in the chat. We probably have time for one or two. I'll go ahead and kick off with one right now. But in your future work, you said that you want to look at, well, let me just see if I understood what you were proposing correctly, that you want to look at maybe families of graphs instead of just comparing the nodes of individual graphs. Is that right?
Yes.
So what do you think the challenges will come up when you're looking at groups of graphs as opposed to just nodes?
So the most challenging stuff is like, so the contrast network analysis, you need to extract the embedding space because you want to compare the same set of features. So the most challenging stuff is like how you can extract the same feature from group of graphs. So even like this is challenging task in network representation learning field. So what kind of method we should design is the most challenging part.
Okay. All right, I see some chatter in the chat here. Let me see. did you test this method on graphs where there was a one-to-one correspondence between the nodes?
Yes, but I didn't include the result in the paper. For example, I tested with two brain networks, which has like both the same like region, so like we can compare together. Yeah, but I wanted to emphasize more strengths. We can compare the graphs which doesn't have like node correspondence each other.
Okay. Well, unfortunately, that's all the time we have for questions this time. So thank you to Natalia Andrienko, who posted that question, and for everybody for attending. Great job, Takanori.
Yeah, thank you.
All right, so this will be Safety Lens, Visual Data Analysis of Functional Safety of Vehicles by Apret Narachenya.
Hello everyone, I'm Arpit, a second-year PhD student from Georgia Tech. Today I will talk about Safety Lens, Visual Data Analysis of Functional Safety of Vehicles. This is joint work in collaboration with Ehsan Kamal from Ford Motor Company and Alex Endert from Georgia Tech. Today's vehicles come integrated with one or many advanced technologies like lane change assist, adaptive cruise control, and parking assist. These technologies have transformed automobiles from mere mechanical machines to complex electronic and software systems. In fact, the cost of automotive electronics as a percentage of the total automobile cost is constantly increasing and expected to touch almost 50% by 2030. If and when these complex systems malfunction, they can be detrimental to the safety of the vehicle, its occupants, and the surrounding environment. In the US alone, there were 6.7 million vehicle crashes reported, of which 0.6% were fatal, 28% led to injuries, and the remaining damaged property. Vehicle safety is important, so much so that in the same year, there were 914 total instances of vehicle recalls by various automobile companies that affected 29.3 million vehicles, costing more than $20 billion. Automotive systems engineering processes involve large amounts of data, many of which are stored in unstructured documents such as Microsoft Excel, and model-based systems engineering tools such as Magic Draw. Using unstructured documents for information exchange is inconsistent, error-prone, and may cause miscommunications. Model-based systems engineering tools, on the other hand, use a common language like SysML that partly solves the problem, but their user experience and functionality is generally focused on creating information. They lack user interfaces for visualizing and exploring data, and they cannot be customized easily to support newer advanced tasks. This encouraged us to apply techniques in visualization on a critical operation in automotive systems engineering called functional safety. Functional safety is a technique in which domain experts identify and assess hazards due to malfunctioning of automotive electronic and electrical systems. They set goals to minimize unreasonable risk due to these hazards and define requirements to achieve these goals. In a 3-month-long user-centered design process, we conducted 1-hour-long semi-structured interviews every week with domain experts from Ford Motor Company. In these sessions, we understood the domain, gathered requirements, defined user tasks, formulated design goals, and brainstormed and prototyped UI designs. We then developed an initial prototype and demonstrated it to 35 domain experts. After incorporating their feedback, we implemented the full system that is now being deployed internally. At a high level, functional safety analysis is a technique that minimizes unreasonable risks associated with hazards. Let us understand this more with an example. Consider this Ford Mustang equipped with the adaptive cruise control system that maintains a set reference speed. Now, what if this feature malfunctions and the vehicle accelerates more than required? This can lead to continued acceleration, which in an overtaking scenario can lead to a collision. Now, to minimize the risk associated with this scenario, a goal to not accelerate the vehicle more than required is set. To achieve this goal, a requirement to be able to override this acceleration with the brake pedal is assigned. This requirement is further assigned another requirement to monitor the brake pedal, which ultimately requires software that compares outputs of brake pedal sensors. There is a technical term associated with each of these phrases. For example, continued acceleration is a hazardous event that can lead to a collision, which is a hazard. Functional safety domain experts determine, implement, and verify these data phrases and their interconnections. This is what a functional safety dataset looks like. The dataset can be modeled as a network consisting of nodes and edges. Nodes have a certain type and a risk level called an ASIL. This ASIL can either be A, B, C, D, or QM, with A signifying lowest risk and D the highest. Nodes can be connected to other nodes of the same type. Nodes can also be orphan, that is, not connected to other nodes. And finally, nodes can also be shared across systems. From our interviews with domain experts, we compiled a distinct list of 25 tasks that they perform. For example, which are these nodes connections? Are any of them missing? Are there nodes that are not assigned an ASIL? These are common tasks that could be accomplished using techniques in network exploration and direct manipulation. Another task is to determine if the risks associated with a malfunctioning behavior are sufficiently addressed. This requires the malfunctioning behavior in question to be connected to at least one technical safety requirement. This task can be accomplished using route tracing techniques in networks. Finally, since automobile systems have many parts in common, domain experts try to reuse node link definitions from other projects rather than re-implementing them from scratch. This fosters better collaboration among teams, saving both time and resources for the organization. This task can be accomplished using techniques in network comparison and set visualization. We then reviewed existing literature in these research areas and used them to guide the design and development of safety lenses, visualizations, and interactions. We implemented rapid prototypes of standard visualization techniques such as the parallel coordinates chart, hive plot, and a dot matrix chart. These designs had a few shortcomings. For example, discovering patterns was difficult in parallel coordinates and hive plots due to the linear positioning of nodes. We finally designed a custom node link group visualization wherein the same typed nodes are clustered using a combination of the multi-body force, circle packing, and collision detection algorithms. Each group is identified with a larger label and its extent is defined as a convex hull and highlighted. Let me now show how safety lens can be used to accomplish the tasks I showed earlier. First, functional safety requires all hazardous events to be assigned an ASIL. While accomplishing this task, let me also walk you through the safety lens user interface. The dashboard view shown gives an overview of the functional safety projects. It serves as the starting point of functional safety analysis. Let us load Project A and switch to the Compare view. The Compare view is the main view of Safety Lens. The project panel shows the selected project as a clustered node link visualization. Each node represents an element in the project. By default, nodes are colored by their ASILs and are grouped based on their types. Each edge represents connections between nodes. Hovering on a node highlights it and shows details in the Detail view on the left. To find all hazardous events that are not assigned an ASIL, we hide all node types except hazardous events. Then, we select all nodes with ASIL hyphen and take a note of it. Next, let us now verify if a path exists from a given malfunctioning behavior or MB to a technical safety requirement or TSR. Let us also verify if the ASIL are all defined and consistent along that path. We switch to the Trace tab, look up a known malfunctioning behavior and set it as source. We pick a technical safety requirement of interest from the visualization and set it as destination. Safety lens finds a path between these two nodes, which can be seen in the visualization as well as the data table below. We now want to compare the end-to-end trace of ASILs right from the malfunctioning behavior to the technical safety requirement. From the table as well as the node link diagram below, we see that the ASILs are consistent. Safety lens also shows a breakdown of ASILs into their severity, exposure, and controllability constituents in the form of a heat map. From this, we find that even though ASILs are consistent, there is some discrepancy in their severity, exposure, and controllability metrics. Until now, we have focused our analysis on exploring a single project. Safety lens also supports comparative analysis among multiple projects. So let us compare multiple functional safety projects and find a project with a node, for example, a malfunctioning behavior, that can be reused in another project. To illustrate this, let us go back to the dashboard view and add two more projects, Project B and Project C. We now see three panels juxtaposed to one another, each representing one project. A new shared view is visible on the left with the nodes and links that are common to the loaded projects. Let's hover on the only system behavior. We see that it is indeed common across all projects, along with a few connected malfunctioning behaviors. Let's hover on one of these malfunctioning behaviors. We can see that there is no edge shared with any hazardous event, which means not all projects have identified the same hazardous event for this malfunctioning behavior. We can see that Project C has many links, whereas Project A has just one and Project B has no link. If required, the analyst could potentially reuse definitions from Project C into both Project A and Project B. We demonstrated Safety Lens to functional safety experts. The overall feedback was positive. One user commented that Safety Lens allows quick detection of problems, but can it allow me to edit and fix the problem within the interface? Another user wanted to visualize the temporal evolution of data. For example, if an ASIL that was previously A is now B. Finally, owing to limited visualization literacy of our users, there was some learning curve involved, especially relating to the several different node colors and their positions. This feedback will help us support new functionality as well as improve the current ones. For more information, please read our paper and reach out to us directly. Thank you.
All right, thank you very much, Arpit. That was really nice explanation of the domain that it was being worked in and how you explored into that space. I have a few minutes for questions still, so please post them in the chat if you have them, just to get things started. Early on, I believe you mentioned that you were going to be deploying a full version of this inside of the, I think you said Ford was your collaborator. Is that right? Did I hear that right?
Yes.
Wow, cool. How are you going to follow up on them after you deploy it to see the impact?
Right, so that's a good point, and we have been having discussions with them about this. So currently so within systems engineering, there are different aspects, beginning from requirements analysis, failure mode effects analysis, fault tree analysis, functional safety analysis, and so on. So this work is the second of such kind. The previous work that we published in some other conference was on failure mode effects analysis. So that is currently being deployed and we are generating data on it.
Okay.
So we'll follow a similar cycle for this one as well. And once we start getting user feedback, we'll actually work on a future version or a revision of this tool. And that's how we can help, visual analysis can help domain experts ensure safer vehicles for us.
I know that's super exciting. Like, I mean, you know, everybody's heard of Ford, and to see it being deployed right there. I mean, that makes me excited for our field.
Yeah, unfortunately, we couldn't show real data because of intellectual property concerns, but they are looking at real data when it's deployed over there.
Yeah, while you were showing the video, I was staring at it, and the closed caption had hidden the warning, data has been obfuscated message for a little while. And I was like, what are these even? Oh, they've been obfuscated. So, yeah. Let me see. Are there other domains besides automotive that you're interested in applying this kind of safety analysis to?
Currently, since I'm working with them, it is focused on automotive systems. Mm-hmm. However, we have received feedback that such a visualization of a node link group diagrams can be used in sensor data analysis or cybersecurity, for example, wherein you can test different what-if scenarios that once we start supporting authoring or editing capability, for example, then let's say I edit a node or establish a link between two nodes, then different what-if scenarios could be tested. That, hey, what happens if I turn this A cell from A to B, for example? Or let me test a network packet along this route, stuff like that. So there are aspects where this design could be generalized, but currently we are focused on automotive systems.
Oh no, that's very exciting. And don't blame me for focusing where you've got people right now. But yeah, definitely some opportunities there.
Thank you.
I'm not seeing any questions pop up in the chat, so I think that we can go ahead and conclude this session. Thank you so much to all of the presenters. This was really great work on graphs. I look forward to seeing more about safety and editing and about human factors influencing algorithm definitions in the future. So yeah, thank you everybody for coming.
Thank you for hosting.
We propose data-driven space filling curves. Our new method generates linearizations that better preserve coherency than existing techniques. Our method supports 3D datasets and even multi-scale data on a quad tree or an octree. Many visualizations benefit from our method. For example, visualization of multivariate particles and visualization
We propose a multi-perspective simultaneous embedding (MPSE) algorithm for visualizing high-dimensional data based on multiple pairwise distances between the data points. MPSE computes positions for the points in 3D and provides different views into the data by means of 2D projections that preserve each of the given distance matrices. MPSE works on abstract data as well as graphs.
Nowadays, data is often distributed and owned by different participants. There is an emerging need to provide a joint visualization, such as a TSNE projection, to serve as the full picture in data analysis. If the participants are privacy sensitive, how can we build a joint projection without data leakage? Conventional embedding algorithms, such as the TSNE, are designed for single-site computation and require data centralization. Privacy leakage may happen in 3 stages in the visualization pipeline.
We present an efficient approach for volume and isosurface ray tracing of structured AMR data on GPU-equipped workstations, using a combination of two different data structures. Together, these data structures allow a ray tracing-based renderer to quickly determine which segments along the ray need to be integrated and at what frequency, while also providing quick access to all data values required for a smooth sample reconstruction kernel.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
VIS has been successfully helping not only experts but also people who want to learn about AI. At VAS 2018, we presented GANLab, an interactive tool for learning about a deep learning model called GAN. But how does VIS help these learners? We conducted 2 evaluation studies, including log analysis of our demo used by over 100,000 people. We will be sharing our findings with you.
Many seamless strategies pay little attention to the preservation of significant contextual structures. In its paper, we propose a context-aware graph sampling method in a vectorized space to preserve not only contextual structures but also significant topological features. Welcome to pay attention to our paper. Its ID is 1259.
There are many similarities between visual analytics and interactive optimization. The design of visual interfaces for optimization systems is an application of visual analytics. However, many optimization systems are automated. If you are thinking of building an interactive optimization system, come to our talk. We have prepared some tips for you.
Being able to perform visual analysis on sensitive data in a privacy-preserving way has become more and more important. In this work, we look at 2 major research questions in differentially private data visualization towards better understanding of the relationship between the privacy parameter, visualization type, the analytic tasks, and users' performance through cross-source, user study, and simulated comparisons.
In this work, we conducted a design study with clinical researchers to develop a visual analytics application for exploring disease progression pathways. As a result, we developed DP-VIS, which seamlessly integrates hidden Markov models with interactive visualizations. The usage scenario and user experiences demonstrate the usefulness of the application to gain useful insights out of disease progression trajectories in a transparent manner.
Traditional flow visualization methods, such as the line integral convolution, convey information about the underlying flow structure. However, the influence of regions in the flow on each other is not visualized. In my talk, I will present a new dense flow visualization technique, creating a multi-level hierarchy that provides insight into the region's connectivity using a probabilistic model. For more specific details, come to my talk.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Do you have a research question but aren't sure how to go about answering it? Are you interested in collaborating with psychologists but want to learn more about how they do research? Our paper presents a comprehensive toolkit of empirical methods organized across 4 categories to help you think about presenting visualizations as experimental stimuli in order to explore and measure how people perceive data. Check out our paper.